Hi everyone, I am Madam Aisha. Today we're gonna learn Chapter 2, Capacitor and Dielectric. We will be discussing three subtopics, which are capacitance and capacitor in series and parallel, charging and discharging of capacitor, and the last one, capacitors with dielectric. Topic capacitor and capacitor in series and parallel. I will introduce to you what is capacitor, what is capacitance, how to recognize the connection, either it is series or parallel connection or circuits, and then what is the equation used to solve the problems. The capacitor is the electrical components. The function of the capacitor is store the energy in the form of electrical charge that produce the electrical difference across its plates. It is made up of two closed conductors. The electrical symbol for a capacitor are like this, or we can draw it like this. Capacitance is the ratio of charge Q to the voltage V we call as the potential difference. The mathematical expansion is following: C equals to Q over V, where Q is the electric charge in either plate, which is the units in coulombs, C. And then C refer to the capacitance, where the unit is farad, F. And V represent the potential difference between the plates, or we call it as a voltage. The unit is volt, V. In order to determine the effective or total capacitance in series and parallel, first, you need to be able to differentiate between these two connections. Okay guys, let's have a look for conductor in our capacitor. So initially, this capacitor or these two conductor plates are in neutral, which have the equally positive and negative charge. When we close the switch, what will happen is the negative electrons will be moving out from one plate to another through the battery. Same goes for another one. These will mix one plate with the positively charged, and then another one will be negatively charged. If I added another two capacitor like this, the charge will accumulate at the both sides. As you can see, the negatively charged in the capacitor 1 meet with the positively charged in the capacitor 2. And then the negatively charged in the capacitor C2 meet with positively charged in the capacitor C3. So this combination we call in series. Meanwhile, if I added another two capacitor like this, the charge will accumulate at both sides as before. As you can see, the positively charged in the capacitor C1 meet with the positively charged in the capacitor C2, and then the positively charged in the capacitor C2 meet with the positively charged in the capacitor C3, and vice versa for the negative plate. Therefore, we call the connection are in parallel circuit. For capacitor in series circuit, the current passing through all the capacitor is the same. So, the same number of charge or electrons have to accumulate. It gives each plate equally charged, where Q total is equals to Q1, equals to Q2, and equal to Q3. Since the potential difference between points A and B or in the terminal is independent of the path, so the battery voltage must equal the sum of the voltage across each capacitor. V total equals to V1 plus V2 and V3. If we substitute V equals to QC in this equation, this will result or end up the new equation, which is 1 over C total equals to 1 over C1 plus 1 over C2 plus 1 over C3. In a parallel circuit, there are only two sets of electrical common points. The voltage measured between set of common points must always be the same at any given time. Or we can say that the voltage drop across each of the branch is the same as the voltage gain in the battery or the power supply. So therefore, we do have an equation of the V total or V effective in the circuit, which is equals to V1 equals to V2 equals to V3, the voltage in the capacitor. Because of the total current in is equal to the total current out, so the total charge QT stored on all capacitor is equal to the sum of the individual charge stored in each capacitor. So Q total is equals to Q1 plus Q2 and plus Q3. If we substitute Q equal to CV in this equation as before, so it will give us another equation, C total equals to C1 plus C2 and C3. When a switch is closed, charge begins to accumulate on the plates, right? A small amount of work is done by the battery to push up the electrons to another plate. So the energy stored in the capacitor is given by U equals to W equals to half Q square over C. If we are substitute Q equals to CV in this equation, you can get another equation of the work done or the energy, which is given by half CV square and equal also to the half QV. Okay guys, now we move to the second subtopic, which is about the charging and discharging the capacitor. So let's have a look at this animation. Okay guys, as you can see, in the plates we do have positive and negative charge equally. But when we attach the battery, what will happen is the electron is moving out from one plate to another plate through the battery. As you can see in the graph as well, in the right side, the value of the Q or charge is increasing exponentially. But you can see also that the flowing of the electrons is getting slower than before, right? So that is because the Q is increasing exponentially to the time t. Now we will refer to the graph currents against time, where here we can see that the charge or the currents is initially in the maximum values. As the time goes by, the values of the current or charge of the electrons are decreasing on one plate, right? So therefore, the values of the current is decreasing exponentially with time. The flowing of the electrons also becomes slower than before. So for charging a capacitor, charge Q against time t, the equation is given by Q equals to Q naught 1 minus exponent negative t over RC, where Q is the charge of the capacitor Q0 is the maximum value of the charge of the capacitor, and then T is the time taken, R is the value of the resistance, and then C is the value of the capacitor. While current against time T is decreasing exponentially with time, so the equation is given by I equals to I0, which is I maximum exponent negative T over RC, where R is the resistance and then C is the capacitor. Now we will have a look for the discharging process. As you can see here, the charge of the electrons is greater compared to another one, so meaning that one plate is positive and the another plate is negative. And notice here that there is no battery in this circuit, so meaning that we are discharging the capacitor through the resistor. So the electrons that accumulates on one plate will be moving to another plate until it becomes neutralized again for both of the plates. Therefore, the value of the charge on this plate is decreasing. That's why on the right side, the graph Q against time T, the graph of charge against T is decreasing exponentially. Now we will be looking for the current versus time, where the current is the moving of the electrons in the circuit. At the first place, the charge is greater on one plate, meaning that we do have a greater current. As time goes by, the values of the charged electrons is decreasing. Therefore, the values of the current is decreasing exponentially according to the time taken. So the graph for discharging a capacitor through a resistor for Q against time will be decreasing exponentially, and then I against time is decreasing exponentially as well. But as you can see in the previous animation, the values or the graph for the currents against time is in the positive direction, right? Here we draw it in the negative direction because the flowing of the electrons is moving from the opposite side from before, which is charging process. The equation for Q against time T is given by Q equals to Q0, which is the maximum charge on the capacitor, exponent negative time divided by RC. While for currents against time for discharging process is given by the same equation as before, but we include the negative sign as indicate the direction of the current opposite from the charging process. But in calculation, you can ignore the negative signs. Do you notice the symbol of tau in the graph? Tau is called as a time constant. The equation of time constant is given by T equals to RC, which is R is the resistance and then C is the capacitance. For the charging process, time constant is the time taken to charge the capacitor to about 60% of its maximum value, while for discharging process, it is the time taken to discharge the capacitor when the amount of charge left on the capacitor is 37% of its initial value. As we discussed earlier, the capacitor is the electrical component. Therefore, the value of the capacitance does not depend on the charge and the voltage, but it depends on the geometry of the capacitor. First, its area between the two plates. The second one, the separation between the two plates. And the third one, the matter present between the plates we call as dielectric materials. When the capacitor is filled by vacuum or air, the capacitance is given by C0 equals to epsilon naught A over D, where epsilon naught is a permittivity of free space, constant 8.85 10 power of negative 12 coulomb square per Newton per meter square, while A is the area of each plate, and then D is the distance between the two plates. In order to get a larger values of capacitance, meaning that your area of the plates must be greater, or your distance between the two plates must be smaller. When the matter present between the two plates, such as a wax paper, glass, or etc., we call it as a dielectric, which is a non-conducting material or insulator. Now, the value of the capacitance is given by C, capacitance, equals to epsilon A over D, where epsilon we call as the permittivity of dielectric material. If the dielectric completely fills the space between the plates, the capacitance increased by a dimensionless factor which called as the dielectric constant. By mathematically, the dielectric constant is a ratio between the permittivity of the dielectric materials to the permittivity of free space. Therefore, a capacitance of a capacitor with dielectric materials now is given by this equation. So we left with dielectric constant multiplied with the capacitance with the air gap. How the dielectric affect the value of the capacitor? Before we insert the dielectric material to the capacitor, what happened is the plates between them is separated by a vacuum. Then we connect it to the battery. Therefore, the plates are charged, one to the positive one and then another one to the negative charge. When we remove the battery, charge on the plates remain constant. Therefore, the electric field will build up between these plates. After we insert the dielectric material between the two plates, the molecules of the dielectric tends to become oriented. The positive one goes to the positive charged plate and then the negative ends pointed towards the positively charged plate. It will end up building of the positive charge on one surface of the dielectric and one of the negative charge on the other. This is how the process of the dielectric effect on a paraplate capacitor. As you can see, after we insert the dielectric material fully, the lines of the electric fields will be cancelled out, meaning that the value of E or electric field strength now is decreasing, as from this equation, as you decrease the values of the E, the voltage of the potential difference between them is decreasing as well. From the equation, C equals to QV, as your potential is decreased, meaning that you increase the values of the capacitance. That's it, guys. Thank you. Till we meet again.